All right, so this is the second and final video on one-way ANOVA for chapter 12. And we're going to look at we're going to look at how R is going to tell us a lot of this information, okay? And we're going to do it through one example from the book, and then I have a bit of a canned example, more of the computations by hand, okay? All right, so example 12.1 in the book, we've got a bunch of different male or boy baby birth weights, all right? And in this example, we're going to categorize the mothers of these baby boys by how old they were when they gave birth. And we're going to have three categories. We're going to have one group of mothers who were ages 15 to 19 years old at the time of the baby boy's birth. Second group, 20 to 24-year-old mothers, and the third group, 25 to 29-year-old mothers. And the question we're asking is, does the birth weight of a baby boy in Illinois differ by the age of the mother, okay? So our null hypothesis is that the average birth weights of babies from group A and B and C all coincide, and the alternate hypothesis is at least one of those pairs is different from each other, okay? Now, in a moment, I'm going to switch over to R and run let me just run the code now. So in the R notebook for chapter 12, I have to screen share. So complicated. Screen share the R Studio. Share. Okay, so classes. Okay, so we've got the R data here. Sorry, the R Studio here. I'm going to just look at the data so you can see what it's like. Make sure I've got my correct packages clicked. And don't, I'm sure. Okay. All right. So here's what the data is going to look like. We have one column for mother's age. We don't know the exact mother's age. It's already been categorized into either 25 to 29, 15 to 19, 20 to 24. And then we've got the weight of the baby boy in imagining ounces, okay? So that's what the data looks like. There's a whole bunch of entries, hundreds of entries apparently. And I'm going to make a table just so we can get a better sense of the data. So I got 44 babies who were born to mothers ages 15 to 19, 90 babies, 20 to 24-year-old mothers, and 107 babies from 25 to 29-year-old mothers. And then I'm going to figure out the mean birth weights in each of these categories, each of these groupings. And if you just look at the data, it looks like the birth weights are increasing as the mother's age increases. So, okay, it looks like there's a difference just there. And then I'm going to calculate the standard deviations. And this is to get the sense of whether that hypothesis that all the population shared a common variance from the first video, that was sort of one of the assumptions we made for the ANOVA process, just to get a sense of whether that seems reasonable. And here, if you look at the standard deviations, they're all pretty close to each other. So they go from basically 411 to 422. So that's not much of a spread in the standard deviations, and that's in the variances. And then I can do a box plot of this data. There it is. And what you notice is that, yeah, the means do appear to be increasing. But it also seems like it might be because of the variability within the groups, right? Like there seems to be a whole lot of overlap between the shaded boxes and the three means. Okay. Right. Well, so now we're going to actually do the ANOVA test. And this ANOVA command is somewhat interesting. I have highlighted. Okay. It's ANOVA and then it's LM for linear model. And I'll talk about that in a little bit on the next panel. But yeah, there's a linear modeling command in there as well. We're going to do weight as a function of mother's age, and then we specify where the data comes from, and we do our output, and we get this analysis and variance table, which apparently I can't highlight. Oh, I can. Okay. All right. And what I'm going to do is I'm going to go back to the board, and this table is copied back down on the board, and we're going to interpret it. All right. So let me stop sharing and go back to panel. Boom, boom. Okay. All right. So here is the R table reproduced. The response variable was weight. And so we had the variable mother's age, and that had 2 degrees of freedom. Because if you remember, there were 3 categories, and the degrees of freedom was G minus 1. So 3 minus 1 gave us 2. The residuals, the formula said it was N, total number of babies, minus G, the total number of groups. So there were 241 babies minus the 3 groups gives us the 238. Then we got the sums of squares, we got the mean squareds, we got the F value, we got the probability, okay? And I'll interpret what these means on the next panel, but this probability right here, this is the probability that the F value, the F ratio, our test statistic, which turned out to be 10.661, this is the probability that an F distribution of the appropriate degree freedoms is greater than 10.661, and we get 3.679 times 10 to the negative fifth. So we get a very tiny p-value, which means that this large ratio could not, virtually impossible that it could have occurred by chance. So we can conclude that there's statistically significant evidence that the true means between the age groups, the true baby weights of boys between the age groups of the mothers are different. So those means not the same. Okay, great statistical evidence to support that. Okay, all right. Now let's go over to the next panel and sort of get a sense of what this table is actually telling us from the formulas from video 1. Okay. All right. So here is the general output that R will give us when we run the ANOVA linear model command. Okay. We're going to have the treatment. So in the last example, that was the treatment is how we make these groups. And we made the groups based on the mother's age. Okay. So there's the treatments, and then there's the error or the residuals. So this is how the data differs from its group mean, the residuals. Okay. So we got the degrees of freedom, the sum of squares. For the first row, that's SSTR, the sum squares of the treatment, which makes sense. For the second row, the error row, it's the sum squares for the errors or the residuals. That should make sense. And then if we add those 2 numbers together, we should get the total sum of squares, which you could check, and we do. Oh, and by the way, if we add these 2 numbers together, we get N minus 1, 1 less than the total data. The mean square then simply scales down the sum of squares by the appropriate factor, which for the F test or ANOVA test is the degrees of freedom. So the first row, we're going to take the SSTR and divide by the degrees of freedom, G minus 1. Technically, then that gives us the mean sum squares treatment. The second row, we're going to take the SSE and divide it by the degrees of freedom, and that's going to give us the mean squared error. This next column tells us the F value, and the derivation from the last video says I'm going to take this fraction divided by that fraction. This is my possibly biased estimator sigma squared divided by my unbiased estimator sigma squared. So we're going to create that F ratio, which is right there. And then this probability is giving me the p-value, okay? And slight recap of the last video, under the null hypothesis, that fraction, that F ratio, should follow an F distribution with G minus 1 and N minus G degrees of freedom. And the p-value is always the right tail to the right of the F ratio, okay? It's the probability that the F distribution could be as large or larger than the ratio, okay? All right, now that R command was ANOVA parentheses LM for linear model. So a slight explanation of why there's a linear model lurking here, okay? So chapter 10, in linear regressions, we attempted to model a linear relationship between the outcome or the response variable and a bunch of predictor variables. For the most part, we were just doing it with one predictor variable, but I did say we could do it with a bunch of different predictor variables, okay? Well, ANOVA is essentially a linear regression where the predictor variables are categories: 15 to 19-year-old women, 20 to 24-year-old women, 25 to 29-year-old women. And what we're measuring is the sum of the squares of the differences between our data and our means, just like we did in linear models. So ANOVA is basically linear regression, where the predictor variables, the input variables, are categorical. Okay, but they're very much related processes. Okay, all right. Both techniques are computing the variability of the response variable from the mean in linear regression, the means in ANOVA. You know, the mean of the first group and the second group and the third group. Okay, all right. So this is the table to keep in mind when you're trying to interpret your R codes. Okay, it's telling you all the ingredients we need for the ANOVA test. All right, so let's do one final example, kind of canned. We're going to do some of it by hand, and we can hand some of it off to R, but we're not just going to ask R to do it all. Okay. All right. So in this example, we've got 3 car dealerships, and they provide to us some data. I've got dealer A, B, and C. Dealer A sells 6 cars, B 4, and C 5 in some given time period. Each dealer tells us the average sale price in thousands of dollars. Okay, so average sale price for the 6 cars from dealer A was $23,800, and for C, the average sale price of the 5 cars was $27,400. And the dealer also tells us the sum square error. So, like here, this would be the let's say J over the 6 cars sold. Take each sale price, figure out the square of the distance from the average of 23.8, add them all together. Okay. All right. So I got the sum square errors for each individual dealer. And then we're also told the total sum of squares was 81.6. Okay. And if you remember, the total sum of square errors was all 15 of these cars, each of their differences from the overall average sale price of all this squared added together. Okay. So we're told that. And we wish to determine whether or not the dealers have whether each dealer's average sale price is the same as the others. Okay, the typical ANOVA one-way question, right? Okay, so we've been provided with a lot of the computational knowledge already. So if we start looking towards the solution, there's what I mentioned earlier, that sum square from each dealer is just telling us this difference for dealer A, for example. So overall, the sum square errors would be the 6.83 plus the 2.75 plus the 37.2, which would give us the 46.78. Okay, so there's SSE. I know there's 15 cars sold. I know we've got 3 groups, 3 different dealers. I also know the total sum of squares is the error sum of squares plus the treatment sum of squares. I was told total sum of squares, error sum of squares are just computed, so we can solve for the sum square treatment sum of squares and get 34.82. Okay, and with that, I think I've got all the ingredients we need to get our F ratio, our test statistic. Okay, so I can make an ANOVA table. So I've got dealer, I've got residuals, degrees of freedom, 3 minus 1 or 2 for the dealer, and 15 cars minus 3 group dealers for 12 for the residuals. There's the sum of squares, the error sum of squares, and the treatment sum of squares. I can divide each sum of square by its appropriate degree of freedom. So the 34.82 divided by the 2, the 46.78 divided by the 12. And then I can take those 2 mean squareds and divide the mean sum errors over the mean sum treatment, and I get my F statistic of 4.466. Okay. All right. So now I need a p-value. I've got my F statistic, my test statistic. I need a p-value. So I'm looking for the probability that an F distribution with 2, 12 degrees of freedom exceeds 4.466. Here is the individual R command. Okay. So I'm going to take the CDF, that's the letter P, the CDF of an F distribution evaluated at 4.466 with 2 and 12 degrees of freedom. So that would tell me the left side, how much probability is less than or equal to 4.466 in this F distribution. I want the right tail, so I do 1 minus, and I get 0.0355, which if we're looking at a 5% significance level, we are below it. So I could say, well, there's good statistical evidence indicating that the mean sale price does in fact differ by dealer. Okay.
It's not overwhelming. I mean, 3.5 is close to 5. It's not like 0.00003. Okay. But at the 5% significance level, we could reject the null hypothesis in this case and say the dealers have different average sale prices.